Good evening. This is Dr. KJ Berry, and I'm here to talk to you about solving problems in fluid mechanics. This is a study aid in the area of Bernoulli's equations and manometry. Fluid or the solution to fluid problems typically requires practice, and no matter what you do in sports or piano or band or any other discipline, to be successful, to be excellent, to be good, you typically have to practice and practice and practice your skills. And to be excellent in solving problems in fluid mechanics also requires a little bit of practice, but practicing the right way, solving problems the right way. And my goal is to provide you with a structured mental approach to solving a series of problems in fluid mechanics. Just like when you practice the piano, you practice a certain format, you practice a certain structure. Just like when you execute marching precision in band, you you will practice certain steps in a certain way, a certain formation in a certain way. So it's that way in almost anything that you do in life to be successful. You need to practice. That's true, but practice to be successful, and practicing steps in the proper way, in the proper sequence, will help you to be successful no matter what you do. So this first problem that I want to talk about is one involving Bernoulli's equations and manometry. We have water flowing from a pressurized tank and through a nozzle, and there's a constriction here. It's exiting from that nozzle, and it enters into a manometer here. And so the purpose of this manometer is to measure the change in pressure. So we have an 8-foot elevation between the tank surface and the exit line here, and a 1-foot diameter section that goes down to a 3-inch diameter section, and the deflection on the mercury manometer is 1 inch. So we have this water which exits from a free jet, and we want to determine the volume flow rate Q, and which implies that we need to find the velocity and determine the air pressure in the space above the surface water in the tank. Well, the first thing that we have to do is really to identify identify the identify and label the points that define the problem. We want to identify the important considerations and understand what what fluid dynamic principles guide the problem. So here we want to identify. We know that Bernoulli is important because we have frictionless fluid flow and a duct. We know that manometry is important because because we are given a manometer a manometer a manometer in the problem. And so we know that the use of a manometer gives us a pressure differential. And we know that mass conservation might be important because we have a change in diameter. So those are keys that will allow us to know, to help us to understand what are the fundamental fluid principles guiding these solutions to the problem. We also have to identify the points of interest, well, not point of interest, but the points that define the different interactions in the problem. So if we have a free jet, such as at point 2, we have a stagnation pressure tap. Point 3 is defined as a stagnation pressure tap. It's important the to identify points that we have a free jet defined. And also, what's critically important is to understand the definition of a stagnation pressure tap at point 3, where the stagnation pressure tap is one where my velocity, the energy contained in my velocity field, is being converted to pressure. So at that point, my velocity is zero, and that's an important observation that will help guide you towards a roadmap to solve the problem. A static pressure tap is 6. We always want to define a static pressure tap above the inlet to the manometer. Very important. Always define a static pressure tap above the inlet to my manometer. And also at the define points at the manometer fluid interfaces. Here we're talking about 5 and 4. So we have a mercury manometer, and we have water above my mercury manometer, and so we have to define these interfaces 5 and 4, and also free surfaces. So we have a free surface which is a point 0.1. So at this point, even before we've put pen to paper or wrote down a single equation, we know that Bernoulli is important because I have fluid flowing through a duct, and it is frictionless. It is steady state. We know that manometry of fluid statics is important because the problem gives us a manometer in the problem, and we understand that a manometer gives us a pressure differential. So step one is always to apply manometry to find the delta P. So the first step is to define the points involved in my manometry equation. Of course, I'm going to go from point 6 to point 3 at because this is point 6, and I want to apply hydrostatics between point 6 and point 3. I could possibly apply it, between, I guess, between point 6 and point 5, or and between point 6 and 4, but that would not give me any useful information that I could use to apply with my Bernoulli equation. So I also want to identify first any unknown dimensions between 6 and 3. So if I look at this problem, the only unknown dimension is the elevation difference between 6 and 5, between 6 and 5 here. So we call that unknown dimension L, because I can go from, because I have no idea of the distance between 6, 2, and 3 and point 5. I know the distance between point 5 and point 4, but I do not know the distance between 6 and 5. So if I apply manometry between 6 and 3, I know that I always start with point 6. I write down my starting point. I always end with my ending point. So the pressure at 6, and going from 6 to 5, I know that this pressure increases as a function of depth. And so this is plus gamma of the fluid times this unknown dimension L, plus gamma sub m, gamma of my manometer. Of course, gamma is the specific weight, and times 1 over 12. So the distance, so I know the distance between point 0.5 and point 0.4 is 1 over 12. I know the pressure is only a function of elevation, not a function of lateral distance. So the pressure here is the same as the pressure at 4. And now going from 4 to 3, the pressure decreases. So that's a negative minus gamma of the fluid times 1 over 12, 1 over 12 plus L. And that has to be equal to the pressure at 3. Note the process. Note the process of identifying the points. Note the process of applying manometry first, and going from 6 to 3 and identifying the unknown dimensions. So I noted, also note that I did not need to define an actual value for L, because gamma L cancels out in my expression. So therefore, my delta P is P3 subtract P6 over gamma the fluid. If I solve this equation for P3 minus P6 divided gamma the fluid is equal to 1 over 12 times the, the ratio of gamma sub m o gamma of my manometer divided by gamma of the fluid minus 1. So the pressure difference, this is what I'm looking for my manometer. I'm looking to find a delta P. Uh, a manometer gives me a pressure difference, and that's what I'm looking to find, a pressure difference between 2 points. So the pressure difference between point 0.3 and point 0.6 divided by gamma of the fluid is 1 over 12 times the ratio of the specific weight of the manometer divided by the specific weight of the fluid minus 1. So now the next step in my logical process is I need to combine this result with my Bernoulli equation. Now that I have a pressure differential in terms of my primary variables. Now I want to be able to use the point the same point that I use with with my manometer for static pressure. And we have to consider which 2 points have the most known information. So I want to apply Bernoulli between point 0.6 and point 0.2, or maybe you say, well, 0.6 and point 0.3. Well, I mean, typically I want to use 0.6 and point 0.3 because of course I have information about that difference. So I want to apply Bernoulli between 0.6 and point 0.3. So therefore, applying the conservation of energy, which is the Bernoulli equation between point 0.6 and point 0.3, and that's why it's so important to write down your points first. We cannot try and solve the problem if we don't know where we're going. So you cannot skip steps. It's important that you write down the points first on the diagram. So therefore, we have P6 over gamma of the fluid plus V6 squared over 2G plus Z6 is equal to P3 over gamma plus V3 squared over 2G plus Z3. I know that we're at the same elevation differences. So therefore, if I can express P6 subtract P3 over gamma of the fluid is equal to V3 squared over 2G minus V6 squared over 2G. But I know this difference here, okay? I have an expression for P6 minus P3 divided by gamma of the fluid. And I know that V3 is 0y, V3 is 0. That's a stagnation point that we identified before. That's also why it's important to use point 0.3 because I know the velocity at 3, it is a stagnation point. So therefore, I can solve this equation for the velocity at 6 because I know that V3 is 0. So therefore, V6 is equal to the difference between P3 minus P6 over gamma of the fluid times 2G. So now my goal is always to get, if possible, one equation and one unknown. So I have an expression for P3 minus P6 over gamma from the application of my manometry. So I always want to normally apply manometry first. Apply manometry first because that gives you a pressure differential that you will apply to other aspects of the problem. So now I need to simply combine Bernoulli and manometry. So I have applied manometry, and I had a ratio that gave me a pressure differential like we derived before. The next step, I apply Bernoulli between those exact same points, and that gave me the velocity of point 0.6. And note that I can replace this pressure difference, P3 minus P6 over gamma, with 1 over 12 times the ratio of my Pacific weights minus 1.0. So that's what we did here. We simply combined these results into the next step. And so if I combine manometry and Bernoulli, I will see that we get V6 is equal to square root of 1 over 12 times gamma sub m, subtract gamma m divided by gamma sub f minus 1.0 times 2g. And so note that I don't plug in numbers. I don't plug in numbers until I get to a point where I see that I have one equation and one unknown. So here I have uh, one equation and one unknown. I can plug in the value of the specific weight of the manometer divided by the specific weight of the fluid. Um, so I can plug that information in, and gives me gives me the value of a V6. V6 is equal to 8.2 feet per second. And so once I know V6, I know my diameter. So the volume flow rate, of course, Q is equal to V times A. And so I know that Q is equal to V6A6, which is equal to V2A2. So Q is V6 times the area, which is pi d squared over 4. And so that gives me a value of my volume flow rate. Q is 6.44 cubic feet per second. And 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 also for mass conservation, I know that once again I can solve for V2 because Q is equal to V2A2. So therefore, solving for my for velocity at point 2 is equal to Q over A2. So I know Q, I know the area, pi d2 squared over 4, and my value of V2 is 131.2 feet per second. So, so what we've done is to as a logical process, applied. First of all, we identified the points. We identified what fluid fundamentals are important to this problem. We know that Bernoulli is important. We know that manometry is important. We identify the points of interest for this problem, and we identify what's happening at the exit points. We know that point 2 we have a free jet. We know that point 3 is a stagnation point. Identifying points where you know you have a free jet is important. Identifying points where you know that you have a stagnation value a stagnation condition is important because at that position you know that V3 that you know that in this diagram that V3 is 0. So those are two important pieces of information that you use and write down up front. So that will help guide you along the road to solve the problem. So the next thing you want to do is find the air pressure. So we apply Bernoulli. I can apply Bernoulli between uh, um, 1 and 2. Some people may say I want to apply Bernoulli between 1 and 6, but I don't know the pressure at 6. So I know the pressure differential at 6. I know the difference between P6 and P3, but I do not know the pressure at 6. So 6 might not be the best option. So if I look at what's happening between 1 and 2, well, what do I know about 2? 2, I know my velocity. at 2 because I just found that from a prior step. And I also know that this is a free jet. Uh-oh, it's a free jet, which means that the pressure at 2 is 0. So immediately I know that the pressure at 2 is 0. I also know that my velocity at 1 is 0 because it's a large diameter tank. So it's the problem said it's a large diameter tank. Well, we know that it's not exactly 0 because we have water leaving the tank, but the velocity of the surface 1 is small relative to the exit velocity at point 2 and at point 2. So it's not really 0, it's approximately 0. But but in terms of the analysis, we have a large diameter tank and a small exit area. So relatively speaking, the velocity of that free surface 1 is small relative to the exit velocity at point 2. So we assume that it is 0 in our calculations. So therefore, I know that I can apply Bernoulli between point 1 and point 2. I know that I have P1 over gamma plus V1 squared over 2G plus Z1 is equal to P2 over gamma plus V2 squared over 2G plus Z2. I know that Z1 is equal to 8 feet. I know that Z2 is 0. That's my datum line. And I know that V1 is 0. I know that P2 is 0. So therefore, P1 can be calculated as if I solve this expression for the value of P1, it's simply V2 squared over 2G minus the elevation difference Z1 times gamma of my fluid. And this information is known. I know the value of V2, and I know the value of Z1. I know gamma of the fluid. And so I know that gamma is water. It's 62.4 pounds force per foot cube. So the pressure at 1 is 16,180 pounds force per square foot, or 112.4 psi. And we also want to find the nozzle inlet pressure P6 here. And if we apply Bernoulli now between 1 and 6, because I never knew the value of P6, now that I know the value of P1, I can apply Bernoulli between point 1 and point 6. And so therefore I have P6 is P1 over gamma plus Z1 minus V6 squared over 2G. And note that the hydrostatic pressure that P6, of course, is equal to P1 plus the elevation differences between 1 and 6, but minus the velocity head at point 6. So so the so the pressure at this elevation 6 is P1 plus the elevation difference, or the elevation head, the potential energy head between 1 and 6. But note that as we increase our velocity, so as my velocity increases as I flow into the nozzle, that decreases my pressure. So pressure and velocity are inversely proportional to each other. So as I increase velocity here, as I increase velocity here, then that means that my pressure has to come down. So it would be incorrect then to say, if I ask for the pressure at 6, just to say that the pressure at 6 is equal to the pressure at 1 over gamma plus Z, right? So if I simply apply the hydrostatic equation, the hydrostatic pressure equation, then I would that gives me that the pressure 6 is equal to the pressure 1 plus the increase in pressure due to elevation. That's the static pressure. But there's another component that contributes to pressure. It's my dynamic pressure. V6 squared over 2g is my velocity head. It's the dynamic component to my pressure because we have molecules moving. So understand that P1 is not equal to P6. P6 is equal to P1, but then because we have an increase in velocity, the pressure decreases as I flow from one along a streamline into my nozzle, um, nozzle at point 0.6. So hopefully from this discussion, I have presented another problem where there's a process of thought in terms of how we solve problems according to a structured logical thought process. And many problems, uh, when we first read the problem statement and look at the geometry, we may not have a clue about, you know, about how to, about what the final result will be. And but you have to be disciplined in terms of, okay, I see my geometry. I be disciplined in how we approach the problem. What's my geometry? Okay, what fundamental fluid principles I've learned applies to this problem? Do I need manometry? Do I need mass conservation? Do I need Bernoulli's equation? How how um, how will this help me solve the problem? What are my important points? You know, do I have a stagnation point? Do I have a free jet? That's very important to in the overall process. You never just want to start writing down equations and seeing what pops out. There's always a logical process, a logical step-by-step mental process that one should follow in terms of solving problems in fluid mechanics and heat transfer and almost any uh, um, uh, uh, any class. So thank you very much, and hopefully you have learned. Hopefully I've been able to help you move one step further in terms of developing a logical, structured process for solving problems in fluid mechanics.